Let me restart. So last time we met, we covered chapter 4. I had essentially covered Newton's three laws of motion, but I didn't really do enough examples. And normally, one whole 3 hour class day in the summer is more than sufficient to cover chapter 4. However, because I didn't do any problems and I spent a lot of time on trying to understand and explain, or excuse me, on trying to help you understand the nuances of Newton's first law, Newton's second law, and Newton's third law, I feel like I probably need to work a couple more examples. So I've decided to work some more examples from chapter 4 and then go into chapter 5. And that's going to maybe put us back a little bit, but that's okay. It's not too terribly big of a deal. I also made an announcement that the face-to-face test one, I still got 5 or 6 students that ended up not being able to take it, and they're finishing it up in one case, or in 3 cases, I think they're finishing it today. In the other 2 or 3 cases, I think they're finishing it up tomorrow or the next day. But I hesitate to announce this because they haven't taken it. But to be honest with you, no matter what they'd score on that, I was still leaning towards doing this. When I looked at the grades and the mistakes that were made on the test, I knew a lot of students who I knew could do better didn't do as well as they should have, or as well as I would have expected them to. And I want the grades to be a little better, and I also want you guys to feel a little bit more confident going into the second face-to-face test. However, the class average on the face-to-face test one was actually pretty good. I've warned you guys that, or I think I've warned you guys that my face-to-face test, the first one, it's not uncommon that the class average be in the upper 40s. I hate it when it gets that low. It's even been in as low as the lower 40s, but it's often in the upper 40s, or at least occasionally it's even the low 50s, which is a little better. But this time, I think the class average was around 65, so that's actually pretty good. But again, I still had a couple students that I didn't think did very well. So my intent is to offer you. It's optional. You're not going to have to do it, but you can. That's why I was freaking out when you guys were typing, I can't, I can't, I can't, I can't. I thought you were saying, I can't take this test, I can't do it. But I'm going to give you ample time, and I'm probably going to give you another offering of face to face test one. And I'm going to allow you to do it uh, with the proctoring service through your computer. So if you have a webcam, then there's an easy way you can do this, and you don't actually have to have a proctor. Hopefully, you all know about that. I'm going to send another email explaining all the details about that, because another thing that was wrong with the face-to-face test one is some people took the online version of the test using the webcam, but because they used a webcam that was mounted to the computer, they didn't technically do it the way it was supposed to be done. If you have a webcam that's mounted to your monitor, then you don't have the freedom of moving the webcam to different places, which is what I need, or I can't rely on a student taking an online test self-proctored. So if you have a freestanding webcam, then you can place the webcam over here or over here in such a way that when looking through the webcam, I can see a little bit of your monitor, but more importantly, I can see your hands, uh, your workspace, which would be in between the edge of your desk and your keyboard and your monitor, and where all the work will be done. So if as long as I can see your hands all the time like that, and I've got access to the actual speakers, and you're not wearing headphones, then I can feel reasonably sure that you're not cheating. The other thing is, of course, you'd have to have all the doors closed, and you'd have to show me where all the doors are, and you have to take the webcam and show me your room, your workspace, everything within lungeable distance to you, and all that good stuff. And any doors that you had to the room would have to be closed the entire time. And if they were to open, then that would be acceptable, but the camera has to be on whatever door opens so that I can see if someone comes in and does anything. So the way we accomplish that is normally we say if you have a webcam that's separate from your, not built into your monitor, you can just do that webcam by putting it off to the side. I would need to see from the top of your, above the top of your head, all the way down to your hands, and I need to see your hands the whole time, and I need to see the monitor and the keyboard and your workspace. If you don't have a webcam that's separatable from your monitor, then what I normally suggest is you just use a mirror Usually like a 8 by 8 mirror is sort of the smallest you could possibly use. Most students use like a full length mirror and they'll just like take it off their wall and stand it up beside them. But in that case, if you had a mirror, you just have it sitting over here. And again, I'd want to be able to see from above the top of your head, part of your monitor, your keyboard, your workspace where you're actually writing, and your keyboard, and your hands would have to stay above the desk, and you can't wear headphones. And again, you're still going to have to take your webcam and show me all the lungeable areas, show me that you have all the doors closed. And of course, as always, if you bring scratch paper into a test, I have to see, if you're self-proctoring, I have to see all sides of the paper very, very closely. So it's, you got to hold it up, but you can't just do it really quickly like that. I need to be able to read every little bit of lines on there, any light writing or something like that. Any violation of any of that is going to be considered a reason for me not to accept the test score. So that's what I'm going to be shooting for. And this will make a lot of people, depending on how I decide to grade it, but this will make a lot of people's grades or make them feel a little bit better about their grades, because I'm either going to set it up where you can only make a better grade or keep the same, or I might make it where you actually have to take a chance, and if you do worse on the second test, you get the second test score. Haven't decided, but I very rarely do that last scenario. It's almost always I'm only going to count the highest of the two scores. So keep an eye out for your emails on that, and let's go ahead and get started. But before we do, does anyone have any questions on any past material? Okay. So yes, I see your things now. Thank y'all for letting me know you couldn't hear me. That was very good. And I should have looked anyways. There's a little audio thing in the bottom left that I don't see the little green thing going up and down when it's not working. So when I saw your can't, I can't. Then I looked over and saw the audio thing was missing. So that was helpful. So thank you everybody for doing that. I appreciate it. Let's go ahead and get started by letting me share my computer screen or my iPad screen with you. So before I jump into this, I want to give y'all one more chance. Does anybody have any lingering questions about anything, but especially any old homework problems or stuff like that? We will have a question and answer session at the end if anybody needs, as I always do. But I just want to make sure nobody has any questions before we get fired up. Okay, well, let's go ahead and get started. What you're looking at here is a parallel to one of the examples in the book. It says, consider a 10-kilogram box resting on a level, frictionless tabletop. A, determine its weight and the normal force exerted by the tabletop. B, if you rest a 40 Newton box on top of the box, what will the normal force be? C, if a friend lifts up on the box with a force of 40 newtons, what will be the normal force? So that's just a chance for you to use the formulas and to use what I explained to you was something called weight, and then the other thing, which was the normal force, which I argued to you that you can see it must exist, because if you imagine, for instance, this calculator laying on my desktop or anything laying on anything, you know for a fact that gravity is pulling down on the object that's resting on a table. So you automatically know that there's a downward force that's pulling on the object resting on the tabletop. You also know Newton's first law of motion, which basically says that an object in motion tends to stay in that state of motion unless acted upon by a net external force. And since the object sitting on the tabletop is not changing its motion, in other words, it's sitting still, it's sitting still, it's still sitting still, that means its velocity is not changing. Its velocity, in fact, is zero. But more importantly, the magnitude of the velocity doesn't matter. It's the fact that the velocity is not changing. And remember, velocity is a vector quantity, so you can change velocity by changing the direction or the speed. You can speed up, you can slow down, or you can change direction. All of those are changes in velocity, and therefore all of those are types of acceleration. And since the box is sitting still, it is not accelerating. That means the net force acting on the object sitting on the tabletop must be zero. And at this point, we only supposedly know the weight, which is the force of gravity pulling down on it. By that, uh, by that conclusion, you have to make, or by that scenario, you have to make the conclusion that there must be some other force acting on the actual object that's sitting on the desk, and that must actually point in the direction opposite the force of gravity so that the two forces can cancel out, giving a net force zero. Well, that force, which acts perpendicular to the surface on which the object sits, is called the normal force. And it's called the normal force because normal is the technical term for a direction perpendicular to a plane. So, if, for instance, the top of my hand is a table and this calculator is an object, then there's a force of gravity acting downward, and then there's a normal force acting upward. And since it's not accelerating, we know that these two forces must add up to be zero, and that's normally how you go about calculating what the normal force is. Last time I hinted at that, but also I did tell you how to calculate the weight. So let's begin by solving this problem. So I use my solution line normally to if I were in a class setting, I might take the time to write down a lot of stuff, but in a online setting, I generally explain it in terms of sentences. That's why the audio, along with the video, is so important here. Notes are not necessarily all that important. So, in fact, it's way more important that you hear in virtually every lecture every day. It's more important that you hear all the words I'm saying more so than getting all the notes. Because as soon as this class is over, I will be rendering these notes that I'm making in a PDF format, and then I'm uploading them to my my Google Docs. I was trying to say G Docs instead of Gmail or instead of Google Docs. So I automatically send them there, so you can have access to the notes immediately after class. And if you miss anything, that's okay. Whereas if you miss the words, you might actually miss really important stuff. And to be honest with you, a lot of times the very things that I'm saying are the most important, more so than the writing. So in this case, I'm writing the solution. What we know is I derived that weight is equal to mass times gravitational acceleration. I know the mass of the box, which I'll call M sub B, is actually equal to 10.0 kilograms. In part A, they want to know what is the weight and the normal force. And F normal equals question mark. Those are two different things that we use to indicate the normal force. It's not unreasonable to see it written as F sub n, nor is it unreasonable to see it written as just an n. Both of those are acceptable, and I flip them back and forth between the two in finding them. In part B, they're going to have an additional force downward because it says if you rest a 40 Newton box on top of the box, what will the normal force be? So what I will say is there's a force B that points downward and is equal to 40.0 newtons. And in that case, they want to know what the normal force is. So I'll say F normal equals question mark. And then in part C, they're going to say if a friend lifts up on the box with a 40 Newton force, what will be the normal force? So in this case, I'm going to say FC points upward. And since these are vectors, it's probably okay for me to go ahead and put a vector symbol on top of them just to indicate it. But by me drawing the arrow and writing the 40 newtons, I think you can see that it has to be a vector quantity, or else why would I give you a direction and a magnitude? So in this case, it's again 40 newtons. So starting with part A, weight is equal to m times g, and in this case, it's going to be the weight of the box, which is 10.0 kilograms, times gravitational acceleration, which is 9.80 meters per second every second. And when you multiply those two, you get 98.0 kilograms times meters per second squared, which is the definition of a Newton, which you could also write as kilograms meters per second. Uh, but I usually don't write it that way when I've got a full Newton. So in this case, I'm just going to call it 98.0 newtons. That is the weight, and I'll say that's the weight of the box, so I'll subscript it B, but that's the weight for part A. Now, the normal force, in order to do that, what we're going to do is imagine the surface is sitting right here, and we don't have to think too much about the surface, and in fact, I'm just going to draw it there, and then I'm going to say that's also the x-axis, and then I'm going to say that the y-axis is pointing up, and what we have is an object with a force acting on it. This force is actually acting in the downward or the negative y direction. And this force is the weight, and its magnitude is equal to 98.0 newtons, as we just calculated. But in order for this box to be sitting on a tabletop and not accelerating, that cannot be the only force. In fact, we know there's one more force, and that other force I'm going to draw in green just to indicate that it's pointing in the positive direction. I see a problem here. Specifically, I tried to save a little room, and that seems to have made it a little less than clear to see, so I'm going to try to move this. Cut, paste. Okay, so what I've done now, I've actually moved it, but I lost my G in moving it, so I'm going to fix that real quick. I got to get my black back so I can write that. So this is the Y, and of course the G came from here. And now I'm going to draw my green force that I was talking about, which is the normal force. And technically, for them to be equal, they need to have the same length. So I'm even trying to go so far as to show the length being about the same. Now this one's going to be called F normal. And what we do is we take Newton's second law of motion for the y direction. We say the summation of the forces in the y direction is equal to mass times acceleration in the y direction. But in this case, the box is just sitting on a tabletop. And the fact that it's just sitting on the tabletop, and then you come back a split second later and it's still just sitting on the tabletop, and it's still just sitting on the tabletop, means that it's not moving. Now, not moving is okay for a split second. That's neither determinant of acceleration or determinant of non-acceleration, but not changing speed over a period of time is a definitive answer that there is no acceleration. And that's what's going on here. So we're going to say the acceleration in the y direction is equal to zero. And now from this free body diagram, that's what this figure is called. It's called a free body diagram, which I'll abbreviate FB D, that's the free body diagram. With that, I'm just going to list the forces. And the free body diagram is key to using Newton's second law. So you got to learn how to use it. And if you're in statics or dynamics, you'll probably find they have acceleration diagrams. Sometimes they have velocity diagrams. They have force diagrams. We in physics pretty much only draw the force diagram. And the force diagram, at least till we get into rotational motion, pretty much takes the object that's experiencing the forces and treats it as a point particle, and then it shows all the forces acting on it. And I'll give you some more advice on how to make sure you catch all the forces, but we can't do that until we understand a little bit more. So now that I have the forces drawn on here, I know and I can tell you these are the only two forces. So I'm going to plug them in. What we have is a normal force pointing upward. So that's basically a y component of a force that only has a y component, and that y component is positive. So the way I'd normally write it would be F normal. I'd write that as a positive, and then I'd say plus. Now the weight has a magnitude of 98 newtons, it has a y component that is negative 98 newtons. So the force that we have on the left-hand side of Newton's second law is the sum of all the forces. So the force that I'm adding is a 98 Newton force, but since we're in component form where I have the summation of forces in the x direction equals mass times acceleration in the x direction, or in this case, the summation of forces in the y direction equals mass times acceleration in the y direction. In these cases, we're really adding those forces, but we're actually adding the components, and the components can be positive and negative. So technically what's going on here is I'm adding a negative 98.0 newtons. That's all the forces acting. And then the right-hand side of the equation, since the acceleration in the y direction is equal to 0, the right-hand side has to be 0. And from that, we reach the conclusion that the normal force is 98.0 newtons. And that's the answer. Okay, so that's how you actually determine the normal forces. Normally, you have to set up a coordinate system, and one of your axes is quite frequently perpendicular to the surface on which it sits, and then any force that the surface is applying to the object that happens to be parallel to that y-axis, which, like I said, is usually normal to the surface and therefore is the right component, that force is the actual normal force. So we normally use Newton's second law to solve for the normal force, just as we did there. Now for part B, they have the same sort of scenario we did there, but they're adding another force to it. So for part B, our force diagram is going to get a little more complicated. So let's draw our force diagram again, our free body diagram. There's my x-axis. There's my y-axis. I'll put the y over here since I obscured it a second ago with the green vector. I'm going to put the box down here as the blue object, and normally on our free body diagram we also draw the mass. We just label it at least. So for instance, if that dot was a full-size object, you could put it inside, but if you're treating it like a little point object, you might have to draw an arrow pointing to it. We already know that in the negative y direction is the y component of the weight, and that weight in magnitude is 98.0 newtons. But now, in addition to that, we are told that you're going to rest a 40 Newton box on top of the box. So what you see is there's another force acting downward on the box, and that force is 40 newtons. So I'm going to draw another red vector since it also is pointing down. And this force is the 40.0 newtons. Now, I just wrote it there. I didn't necessarily write a symbol or anything like that because I didn't really need to. All I needed was a number, but I did write it kind of small, so I just zoomed in to make sure we can write it bigger. So that's the other 40 Newton force, and it's not exactly the scale. Obviously, 40 newtons would be a little bit smaller than half the length of the 98 newtons. So if I wanted to, maybe I could extend it this way, and that gets a little closer. But it's close enough. The main thing is I just wanted to show that it's clearly less. Now, in addition to that, because both of these forces, the force on the top of the box pushing downward and the force of gravity pulling downward on the box, both of those are being fought by the force provided by the table. You don't necessarily see that, but if you would imagine instead of putting a 40 Newton box on top of it, but rather putting an elephant on top of it, you'd quickly see that the tabletop would fail in that sort of force scenario, and you'd realize, oh, there must have been some force because now we've exceeded the ability of the table to sustain the force. So we're now going to have a normal force that again points upward. So I'm going to draw it green, and we don't really know what it is, so I'm not trying too hard to draw it completely consistent with what its size is. I know because I've been doing this for years that it's going to be basically 58 newtons, but I'm going on the assumption that you don't necessarily know that now. So now we're going to do the summation of forces in the y direction is equal to mass times acceleration in the y direction, but the acceleration again is 0, so the summation forces in the y direction equals mass times acceleration in the y direction, with the acceleration going to 0. In this case, it gives us Fn plus negative 98.0 newtons plus negative 40.0 newtons is equal to 0. And from that, we get F normal for part B is equal to, what we're going to do is pull the 40 to the other side, or we could just go ahead and combine like terms. And in this case, ooh, actually, I said 58, but I was remembering the other part, not this one. Sorry. So completely ignore that 58 I said a second ago. But what we're going to do is we're going to add the negative 40 newtons and the negative 98 newtons, and that's going to give us negative 138 newtons. But then I'll put it on the other side, so I'll get Fn is equal to 138.0 newtons, and that's correct even to the proper number of sig figs. Anybody have any questions on that one? Now we can do part C. It doesn't look like we have any questions. Let me pull up the chat just to make sure. All right, we got that. So we're in the main chat. Looks like no one's posted a question. Okay. So now I'm going to do part C, and I'm going to fit it right in this little area. We're again going to have a free body diagram, which I'll draw my coordinate system like this. There's my x-axis. There's my y-axis. Here's my box. 10.0 kilograms. Oh, that was really the most horrible written 10 kilograms I've ever written. So I'm going to fix that. And this is supposed to be my x-axis that I just mutilated quite a bit. And this is the 10.0 kilogram mass. We have acting on it again a weight that acts in the negative direction. And this weight has a magnitude W equals 98.0 newtons. That's technically the Y component. So that quantity, the Y component, is in fact negative. Now, in this case, they're saying if a friend lifts up on the box with a force of 40 newtons, what will the normal force be? So in this case, I've got to break out a green vector to show the part where the friend is lifting. So I'm going to call this F sub C, and its magnitude is 40.0 newtons. But then in addition to that, I'm going to have a normal force, F normal. So again, I'll use the summation of the forces in the y direction is equal to mass times acceleration in the y direction. But again, the acceleration in the y direction is 0. This time, I'm going to actually have Fn minus 98, which is the same thing as plus a negative. I'm just writing it a little easier this time. So it's minus 98 newtons for the plus negative 98. And then it's also plus 40 newtons equals 0. Now, I ended up writing that so small because I'm trying to fit it in. So let me zoom in and show you exactly what I wrote. What we have here is the 98 newtons. Oh, is the 98 newtons that points downward. So rather than taking the time to write plus negative 98, I just wrote minus 98. And you can see that in this case, I'll take the negative 98 plus 40. They're like terms, and that gives you negative 58. And then I put the negative 58 on the other side, and that tells me that the normal force is positive 58.0 newtons. And that's because it was negative 58 on the left side, but when I pulled it to the right side, it became positive 48. So this is an exercise trying to show you about the things that affect the normal force. So, for instance, when you take an object and you lay it on the ground, the weight, if the ground is perfectly level, the weight will be equal in magnitude to the normal force. But if you do something else to push down on the box, then the normal force will get larger. Similarly, if you do something else, but in this case to lift up on the box, then the normal force will get smaller. What we'll also discover is that when the force of gravity is not perpendicular to the table or to the surface, in other words, like an inclined plane or something like that, we'll find that then the normal force is also not exactly equal to the weight anymore in magnitude. So those are the things that can affect it, and that becomes very important because later on, what we'll learn is when we learn friction, when we learn about friction, friction is actually directly proportional to the normal force or can be up to directly proportional to the normal force. So that's why we need to be able to calculate the normal force so that we can make use of friction later. Does anyone have any questions on these problems? Okay. Well, let's move on to our next example. It says the weight of the 10-kilogram box from example 1 was 98 newtons. What happens if you lift up on the box with a force greater than 98.0 newtons? And then I put in parentheses, let's say 100 newtons, just to be concrete. Okay? So the solution on this case involves the same stuff that it did before. We have weight is equal to mg, which in this case we're already told was 98.0 newtons, and we also knew that from doing the previous example. But in this case, we're going to try to push up on the box or lift up on the box with a force F. I'm going to say is up, and I'm going to say it's 100.0 newtons. So now I'm going to draw another free body diagram for this one. There's my x-axis. 1, 2, 3. Let's see. This is my y-axis. There's my mass right there. That is 10.0 kilograms. Now I have a force acting downward. That force is the weight, and the weight is equal to 98.0 newtons. But now what's going to happen is we're going to apply a force in the upward direction of 100.0 newtons, and that's going to be F. So what we're asked here is what happens when this happen when you actually apply these forces this way. Well, according to Newton's second law, the summation forces in the y direction is equal to mass times acceleration in the y direction. I can't jump to the conclusion that the acceleration in the y direction is zero because I don't really know whether it's moving up and down or if there's any kind of acceleration upward or any kind of acceleration downward. All I know is that these are the forces acting on it, and it's Newton's second law that determines what happens next. So I have to do the left-hand side of Newton's second law, and the left-hand side of Newton's law says that 100 newtons is acting in the upward direction, so I'm going to say 100.0 newtons. And technically, just by writing that as a positive, that tells us that the y component of that force is acting in the positive direction. And then, of course, the left-hand side of Newton's law, Newton's second law, is a summation of all the forces. So I'm now going to add the y component of the weight, which in this case is negative 98.0 Newton. Now notice as the semester goes on, I'm not going to waste time to write the plus and then put a minus after it. I'm going to just start using minuses, but I want you to realize that it's not that Newton's second law says that we're adding and subtracting various forces. Newton's second law always says add all the forces acting on the body of mass m and put those on the left-hand side of the equation. And then on the right-hand side of the equation, you have the object's mass times the object's acceleration. It's just a matter of the components when we break Newton's second law from a vector equation, which is the summation of the vector forces is equal to mass times the vector acceleration. If we break that down into a equation for the x direction, equation for the y direction, equation and an equation for the z direction, then those equations are about components, not about vectors, and components can be positive and negative. So that's what's going on here. These are all the forces that are acting on it. You might think, well, what about the table? Well, guess what? Once someone puts enough force on it where the normal force is not needed, then the table is not going to apply any force to it unless it had some kind of sticky glue or something on it that was holding it down. They didn't tell us anything like that, so we can't make that conclusion. So I now have the left-hand side of Newton's second law written down. I'm going to write the right-hand side, and that is 10.0 kilograms. Now, I'm just going to write that as times A instead of A sub y because the only motion that's even remotely relevant here is the y direction because there's no forces in the x direction. All the forces we have drawn on the free body diagram are in the y direction, so there's only one direction we're dealing with, that is the y direction. Why waste the time to write A sub y? All right. But in doing that, what we discovered is that 100 newtons plus negative 98.0 newtons is 2.0 newtons. And of course, my note taking program all of a sudden just turned my pencil into an eraser. So that's super helpful. So it's positive 2.0 newtons is the left hand side is equal to 10.0 kilograms times A. So what we discover is that A is equal to 2 divided by 10. And of course, 2 divided by 10 is 0.200. Now, technically, I'm taking a two-digit number, a 2 sig fig number, the 2.0, and dividing it by a 3 sig fig number, the 10.0. And the rules of sig figs tells us that when you divide two numbers of differing significant figures, the one with the least number of significant figures tells you how many significant figures to round the answer to. So that's why I underlined that second zero. But the answer is, remember the Newton was a kilogram meter per second squared. When you divide that by a kilogram, you just get meter per second squared, which I've advised you guys to write meters per second per second. So what actually happens in this scenario is that when you apply a force upward that happens to be bigger than the force of gravity, then you actually provide enough force for it to overcome the force of gravity and the object will accelerate. And that's basically true anytime you get a answer that's different from zero on the left-hand side of Newton's second law. So when the sum of the forces on the left-hand side equals something other than zero, then you're going to get an acceleration. And if the summation of the forces on that left-hand side is negative, then that acceleration will be in the negative direction along that axis. And if it's positive, it's going to be in the positive direction along that axis. In this case, we were drawing in along the y-axis, so this is an acceleration in the upward slash y direction. So I can put upward there just to indicate exactly what direction that is. And by doing that, it's now okay to say this is the vector A equals 0.20 meters per second upward. If I didn't include that upward, it would technically be incorrect to write a vector symbol over the A. Anybody have any questions on that? Okay. Now this one gets a little bit more complicated, and I left another page after this just to make sure I have plenty of room. But it says a 100 kilogram person descends in an elevator that briefly accelerates downward at 0.200 g. The person is standing on a kilogram scale. That means a scale that reads not pounds, not newtons, not slugs, but kilograms. A, when accelerating, what does the scale read? And B, what about when the elevator descends at a constant 1.75 meters per second downward? So that's the questions that we're trying to answer. I'm going to go ahead and draw a coordinate system. I'm going to first draw a picture to let you understand what we're talking about a little bit here. So I'm going to imagine an elevator like this as a box, and in this elevator is a scale, and on that scale stands a person. And that's what we're looking at, only in this case, the acceleration is downward and it's 0.200 g, which equals 1.96 meters per second downward. Double checking my math because, when you're actually, well, it's just like I was telling my students the other day, when you're reading out loud, I don't retain, I don't retain any information when I'm reading out loud. Similarly, sometimes when I'm talking out loud, I don't necessarily think well enough about the things I'm doing, which obviously makes it really hard as a teacher. But anyway, what 0.200 g means is it's not 0.200 grams, because that wouldn't make any sense because we're calling it acceleration. So in order for it to make sense, the g must refer to gravitational acceleration. So if I take zero point 0.2 and multiply it by 9.8, I get 1.96, which is what I suggested, and that is correct. So the acceleration is going to be downward at 1.96 meters per second every second. And again, what that acceleration, and the reason why I'm saying it's meters per second each second, means that if we drop this elevator box downward and ignored all the resistance, air resistance, friction, and all that stuff, while it was accelerating at 1.96 meters per second, what that means is if you dropped it at a velocity of 0, then at t equals 0, it would be going 0 meters per second. But exactly 1 second later, it will be going 1.96 meters per second downward. And exactly 2 seconds later, it would be going another 1.96 meters per second. So it'd be 2 times 9.8 meters per second. And then after the third second, it'd be going another 1.96 meters per second. So that would be 3 times 1.96. Okay, so that's what that means. Now for the free body diagram, there's a couple scenarios. The A one is the one I'm sort of drawing right now. So here's my x-axis. Here's my y-axis. And all I'm doing is I'm imagining sort of the equilibrium, if you will, of the little stand that the person is standing on. I didn't mean to draw that with that. This little part right here of the scale, that's sort of what I'm thinking about the equilibrium of, just because it makes it a little easier to think this way. Uh, you can think about this and say there's a force acting downward. That force is the force of gravity. And it's the force of gravity specifically on the human, and the human has a mass of 100 kilograms. So weight human, let me write this in a different color here. So the weight of the human is equal to mg, which equals 100.0 kilograms times 9.80 meters per second every second. That's going to give me 980 newtons. So in this case, I'm going to say right here, I have a force acting downward, and that force is the weight, which equals 980 newtons. Now, in addition to that, the scale has to be supplying a force upward. So I'm going to call that force the F sub S for force of the scale. And I'm going to use green again for the upward direction. So I'm going to say this is F scale. And the F scale is really what we're looking for, sort of. The F scale is going to come out in newtons, but this is a kilogram scale, so I then got to divide it by 9.8 so that I can make it into a mass as opposed to a weight, or as opposed to a as opposed to a weight or a force. Now, in addition to that, what we understand is the acceleration is downward at 1.96 meters per second per second. So, with all this in mind, I can say the summation of the forces in the y direction equals mass times acceleration in the y direction. Now, what I see is the force that's acting upward. That's the one I'm going to call positive. So I'll write F sub S plus. Now I have to add the force that's acting downward. That's negative 980 newtons. Again, as the semester goes on, I'll stop writing plus a negative and just write minus. But right now I'm not doing that. And now I'm going to say all of that is equal to basically the weight of the person, okay? Or excuse me, the mass of the person. So we're going to put the person's mass there because that's really, even though we're sort of focusing on that little thing right here, that's sort of the equilibrium we're thinking about. We're still talking about the human moving, so I have to put 100 kilograms because that's the human's mass. And then the acceleration in this case is going to be in the downward y direction. So that's negative 1.96 meters per second per second. Since it was downward, that's where we got the negative. Now, what you can see is this becomes negative 196. That's the actual math of multiplying these two. And that's to the proper number of sig figs because we only had 3 sig figs for the 1.96, even though we had 4 for the 100. So this allows me to solve for the scale force, the force that the scale is applying. So I'm going to write force scale, or F sub S, is equal to, notice it's negative 196. 0.0, that's not a significant figure. And now I'm going to add a 980 to both sides, so this will be plus 980.0, again, adding a non-significant digit to that. I'm going to say 980 minus 196, and that gives me 784.0 with an underbar newtons. Now, that is the force that the scale is feeling, but the scale has been calibrated so that it interprets that force as a mass given by the force divided by 9.8. So that means the force of the scale in kilograms, even though it's a bit of a misnomer to even call it a force, is going to be 784 divided by 9.8. And when I work that out, I get 80. So uh, the scale reports that the person is, in fact, 80 kilograms. So that's the answer to part A. Anybody have any questions on that? Now, hopefully, you've all tried this. If you haven't, you just haven't had as quite a fun life. In fact, I do this even with my daughters to this day, even they're in their 20s now. But if we get on the elevator and no one else is on it, I immediately, as soon as we start to take off, if we're going to go downward, I jump up because I know it's going to accelerate downward initially, and because it's falling downward, my apparent weight is a little less, so I can jump up and my head can come really close to the ceiling. And I'm a fat white dude, and it's very rare that my jumping leads to my head getting anywhere close to a ceiling. So that's kind of exciting. And then as I get to the bottom, I know it's going to be accelerating upward because it's going to be slowing down as it's going in the downward direction. So that's an upward acceleration. And therefore I can take and sort of allow my legs to be a little loose, and I'll feel my whole body be compressed down into the floor. Or sometimes I'll try to jump and see that I can't jump at all. So that's the difference. If you were actually trying to consider it with an acceleration upward, you'd get the same numbers except the negative 1.96. If you chose the 0.2g again, but it was accelerating upward, that would be a positive 1.96, and then you'd be adding the 196 to the 980, and that's why you feel heavy when the elevator comes to a stop on the way down. On the way up, when the elevator comes to a stop, you feel light. That's why I jump up. On the way down, you feel heavy. So now let's go to part B. It says, what about when the elevator descends at a constant 1.75 meters per second? So, oops, I did not leave myself enough room. But I can tell you the answer to this. Now, remember, even though we're moving at a velocity, that might throw you, and that's exactly why we asked this question, 1.75 meters per second downward. It's going 1.75 meters per second downward, but if you wait a split second, it's still going 1.75 meters per second downward and still 1.75 meters. So it's not accelerating at all. That means in this equation, the acceleration is zero. Because the acceleration is zero, you get the normal force is just going to be equal to the weight. So for part B, F scale equals, now in this case, it's 980 is the force. I got to divide by 9.8, and that's going to give me 100.0 kilograms, excuse me, as what the scale will read in part B. So hopefully that makes sense. Anybody have any questions on that? Okay, let me work one more problem and then I'm going to give you guys a break. The problem I'm going to work is this one right here. It's actually pretty straightforward. It's not bad. That's why I decided to do that before the break. It says, example 4, consider the figure below and calculate the sum of the two forces exerted on the boat. So that's supposed to be like water between two docks or two banks. So those black lines with the little hash marks on them, they're like the bank of a river or a bulkhead, or actually a walkway on top of a bulkhead on each side of a river. And you can imagine that those black lines are actually ropes, and they're pulling the boat forward in one case at 40 newtons at 45 degrees uh, upward from the x-axis, and in the other case at 30 newtons downward at 37 degrees uh, from the positive x-axis. And what we're asked to calculate is the net force. So really what we're doing here is we are adding two forces. So solution, I didn't necessarily ever write this down. Your book does have it, but I explained how to add vectors. But now I'm going to tell you that the sum of two forces, let's say A plus B, if you call S the sum of vectors A and B, then S sub x is equal to A sub x plus B sub x, and S sub y is A sub y plus B sub y. And of course, if you had a z-axis, you'd have that too, but this is only a two-dimensional problem. But that's really what we're going with, is we got to break these vectors down into components. So I'm going to take my time to break them down into components so you can see exactly what's going on. In this case, I'm going to use black again as my coordinate system, and I'm going to draw the x-axis as positive to the right, and the y-axis is positive upward, and I'm going to draw that top force on this diagram as this force right here is 40.0 newtons, and this angle right here is 45.0 degrees. Now, what I do to try to figure out what my components are is I imagine starting at the tail of the vector and going to the head of the vector only by going routes parallel to the axes. So if I were, for instance, to try to go in the from the tail to the head, and I first chose to go along the x direction, then I would have to go to the right. And by going to the right, I see that that is in fact a positive x direction. And then that was my attempt to leave the tail to go to the head parallel to the x-axis. Now all I have left is a route parallel to the y-axis, so I have to go up or down. I can see in order to get to the head of the vector, I'm going to have to go upward, which is another positive direction. So that is also positive. So now I know the x component and the y components of the top vector are in fact positive. And as I told you, until you take the training wheels off, it's probably best that you write out sine of the angle and cosine of the angle and then solve for the x component and the y component. So what I know is sine of 45.0 degrees. I happen to know that's equal to the square root of 2 over 2 because it's uh, well, just a common normal angle for trigonometry. But I also know that some old horse is the mnemonic, or so is the mnemonic we use for sine. So sine has to be opposite over hypotenuse. Remember, the opposite side is the side that's not touching the angle. The adjacent side touches the angle and is not the hypotenuse. And the hypotenuse is the side that if you draw the right angle, it looks like an arrowhead pointing to the hypotenuse. So see how that makes an arrow pointing to the hypotenuse? So some old horse or sine equals opposite over hypotenuse gives us that the opposite side would be the y component. So I'm going to say F, and I'll call this T for the top force, Ft sub y over the hypotenuse, and the hypotenuse is 40.0 newtons. And of course, that means Ft sub y is equal to positive. Notice I put that sign there. You don't have to put it for a positive, but trust me, you definitely have to put it for a negative, and you need to put it whenever you're doing the trig functions this way, where you're just choosing the angle that's probably smallest because it's between the vector and the nearest axis. So it's not uncommon for me to use the angle between the vector and the y-axis, the angle between the vector and the negative x-axis, or the angle between the vector and the negative y-axis, all that good stuff. And then I use my understanding of components to figure out whether the components are positive or negative. In this case, what I'm going to do is take the 40 newtons and I'm going to multiply it by the sine of 45 degrees, making sure my calculator is in degree mode, which it is, and that gives me 28.28. Whoop. That gives me 28.28 newtons positive, and I only had 3 sig figs for the sine, so that should have spit out 3 sig fig, I mean for the angle, so the sine should have spit out 3 sig figs, and the 40 newtons had 3 sig figs, so multiplying 3 sig figs by 3 sig figs gives me 3 sig figs, and that's why I underlined the 8, the second 8. Now I'm also going to do cosine, and the cosine of 45.0 degrees, remember, is came a hopping, which is cosine equals adjacent over hypotenuse, or ka in so ka toa. So in ka, it's adjacent over hypotenuse, and the adjacent is the x component, so I'm going to call that F top sub x. And then the hypotenuse is 40.0 newtons. Therefore, Ft sub x is equal to positive. Now, because sine and cosine actually are the same thing at 45 degrees, we're going to get exactly the same answer. So it's 28.28 newtons positive for the x component. So notice by writing the sine and then writing the cosine, I could have first looked at the sine and the cosine and figured out, oh, the sine is going to give me the y component and the cosine is going to give me the x component. And if you always took the angles in the standard position, which was measured counterclockwise as positive from the positive x-axis, then the x always gives you the the cosine always gives you the x component, and the sine always gives you the y component. But there's a lot of ways to make errors there, so I'd advise against that. Now I'm going to draw the other vector. I'm going to actually draw it. No, I'll draw another coordinate system just to keep it from getting so messy. But this time I'm focusing more on the lower y-axis. In other words, the negative y-axis, like this, and this is my x-axis. And this time the angle is actually not uh, 45 degrees, but 37, which you might recognize as one of the special angles for the 3-4-5 triangle. That's what we're shooting for here. So this is the 3-4-5 triangle. That means that I can take the force, and since it's 37 degrees, I can go over 4 and then up 3, and that, or excuse me, over to the right 4 and then down 3. And that's roughly where the, vector should point. So I'm going to draw the vector that way, where I go to the right 4 and down 3. And that assures me that this angle right here is precisely drawn as 37.0 degrees. It's technically not even 37.0, it's like 36.87 degrees is what the 3-4-5 triangle. So that's really close enough. Now, again, I imagine going from the tail of the vector to the head of the vector by only traversing parallel to the x-axis and parallel to the y-axis. So if I first do the x-axis like I did before, I'll see that the x-axis is going to require us to go in a positive coordinate direction along the x-axis, so that the x component is in fact going to be positive. So that's a positive x component right there. But the y component is in fact a negative component. So I'm going to draw it downward, and that one's negative right there. Again, write out the sine of 37.0 degrees equals opposite over hypotenuse. In this case, it's going to be FB for bottom, y component over 30.0 newtons, because this is 30.0 newtons as drawn in the diagram. And now I draw the cosine. The cosine of 37.0 degrees is equal to F bottom. In this case, it's adjacent, so that's the x-axis over the hypotenuse, which is 30.0 newtons. And this means that FB sub y is equal to, notice, or excuse me, FB sub y is equal to a negative. So I put the negative there, and I'm just going to take 30 and multiply it by the sine of 37. Now remember, the sine of 37 is not exactly the sine of 36.87, so it's not going to come out exactly the same. But in order to show you exactly what it comes out, then it's smart for me to actually type in the sine of 37. And that gives me negative 18.05 newtons. Similarly, I can take 30 times the cosine of 37, and that's going to be FB sub x, but the x component is positive. So in this case, I'm going to take 30 times cosine 37, close parenthesis, and that's 29.997, which rounds to 30.0. Whoa, it can't round to oh, can it? Oh, no problem. I ended up pushing cosine twice. I don't know how that happened. Let's see, 30 times cosine 37, close parentheses, that's not 20. Okay, so that's 23.96 newtons. Again, I underlined the non-significant digit. Now that we have that, the sum of these two forces, S, is equal to F top plus F bottom. Therefore, S sub X is equal to the sum of the two X components. So that would be positive 28.28 newtons plus, now that was the top one. The bottom one in terms of X was positive 23.96 newtons. So I'll say 23.96 plus 28.28 gives me 52.24 newtons, and that's in the positive direction. Now the y component of the sum, S sub y, would be the positive 28.28 y component of Ft. So that's positive 28.28 newtons. Plus, now I have to add the y component of the bottom one. That y component is negative, so I'll write negative 18.05 newtons. And that is 28.28 minus 18.05 gives me 10.23 newtons, which is also positive. So now what I have is an X component that's like 52 in the positive direction and a Y component that's like 10 in the positive direction. So if I draw another coordinate system really quickly, there's my X axis and there's my Y axis. Then what I have is a X component that's really, really big and positive. So I'm going to draw it like this. And this is S sub X equals 58 point, or excuse me, 52.24 newtons. And then the Y component is going to be quite small, but also positive. So this is S sub Y is equal to 10.23 newtons, again positive, so that we see the sum of the two vectors, which I'll draw in blue, is just this vector right here, and this angle is phi. So S will have a magnitude that's equal to the square root of 10.23 newtons squared plus 52.24 newtons squared. Now you got to be careful when you're doing additions and squarings. You've got to figure out exactly where all the sig figs go. So when I do 10.23 and I square it, I know I have 3 sig figs, and that answer is 104.6529. Since I only have 3 sig figs, that means that that answer is only good to the ones place, because 1, 0, and 4 is 3 sig figs. Now when I do 52.24 and square that, I know that one only has 3 sig figs, and that's 2,729.0176. That means that one's only good to the tens place, because 3 sig figs gives you just the 2, the 7, and the 2, but the 9 before the decimal place is not significant. So when I add these two, 104 and 2729, and I'm adding all the digits, by the way. This 104.6529 plus 2729.0176, that gives me 2,833.6705. And remember, that's only the tens place, the hundreds place, and the thousands place that are significant. And then I got to take the square root of that, and that gives me 53.23. But again, that's only 3 sig figs, so the magnitude is 53.2 with a 3 after that. That's not significant, so that's the magnitude. And the phi is equal to the inverse tangent of the 10.23 over the 52.24. And that gives me shift tangent inverse 10.23 divided by 52.24 close parentheses. That gives me 11.07 degrees. Actually 11.08 degrees. So my final vector really is that. It's roughly 11.1 degrees above the x-axis, and the magnitude is 53.23 newtons. In fact, I can write the answer as S equals sum is equal to 53.2 newtons at 11.1 degree. And that is completely without ambiguity, because remember, when I say at, then if it only says at for the angle, then I have to assume that the angle is in standard position. And standard position means if the angle is positive, it's measured counterclockwise from the positive x-axis towards the positive y-axis. If it's negative, it's measured clockwise from the positive x-axis to the negative y-axis. So that's the whole sum of these two forces. Does anybody have any questions on that? No questions? I was trying to look at the answers the book got. The book got 53.3 for the magnitude, and it got 11.0 degrees for the direction. So that looks exactly like the answers we got, and we can be a little confident that it's correct. Let's go ahead and take a 10-minute break. Be back at 6. Be back at 6:55. I'm here the whole time, so anybody that has questions, you're welcome to ask, but you're not required to stay here. You can go get something to drink or whatever. I just heard a voice. Did somebody say something? It might have been in another room, but I was afraid maybe I just had the volume down too low. It looks like not. No, I'm good. Right back. All right, got about 2 more minutes. We have about 2 more minutes, everybody. The reason I left is to get my tea, and then I left it over there. No, I got it. All right, it's time to get back started. Does anybody have any questions on the force problem that I just worked through? So I want to point out that we found that the sum of the forces, this would be, if we were doing a Newton's second law problem, this would be the left-hand side of Newton's law. The summation of the forces would give you 53.2 newtons at 11.1 degrees. Okay. Now, what that means, since Newton's second law is a vector equation, the left-hand side, the summation of the forces as a vector, is equal to mass times acceleration, which is also a vector. And of course, if you multiply a vector like a, the acceleration, by a scalar m, which is positive, then you don't change the direction of the vector a at all. Well, since the vector m times a has to be equal to the sum vector, the sum of all the vectors, in other words, that means the direction of a is the same as the direction of the force, as the total force. So the acceleration of this boat, assuming this is all the forces that are acting on it, which is not necessarily the case, but possibly could be, the summation of the forces being 53.2 newtons at 11.1 degrees suggests that the acceleration is going to be 11.1 degrees as well. Now, if you wanted to know the magnitude of the acceleration, you'd have to take the 53.2 newtons and divide it by the mass of the boat. And that would give you the actual magnitude of the acceleration, but the direction would be 11.1 degrees. So hopefully that makes some sense. Anybody have any questions on that? All right, well, let's go ahead. I've drawn up a couple other examples that I want to solve for you. Does everybody understand how we were able to use Pythagorean theorem to figure out the magnitude, and then how we use an inverse tangent to find the angle? This is all stuff that you should be able to do at the drop of a hat from now on. Literally on the last day, even if you took 241, 242, and 243, which would be the third semester of this course, I would not be surprised to find on the very last day of the third semester you're still adding vectors. So this is not a thing that's going to just go away. It's not one of the few little areas that you can sort of, well, I don't necessarily understand that part, but I get everything else. No, if you don't understand this part, there's a good chance that you're going to fail. And if you don't, you should fail because it's still going to harm you next semester when you take 242, or the next time when you take 242, and the next time when you take 243, and the next time when you take statics or dynamics, or all the other things that you're going to take for engineering, or physics, maybe some stuff for chemistry too. So, anyways, that's just a warning. I want to make sure you guys know that the vector thing, adding vectors, subtracting vectors, adding them graphically, subtracting them graphically, multiplying them by scalars, writing them in terms of ij's and k's, or writing them in terms of x hat, y hat, and j hat, and k hat, and I hat, and all those things. All those are never going to go away. So let's go on to example 5. It says, what is the normal force in the diagram below? So what we have here is a 20 kilogram box sitting on a table. Okay. I'm not saying the thing is accelerating, but I am saying it's definitely not accelerating upwards or downwards. So the acceleration in the y direction is equal to zero. This force might actually cause the object to accelerate to the right. There might not be sufficient friction to keep the 20 kilogram box sitting still, but all of that's completely immaterial. All we need here is to find the normal force, and looking at the diagram and having it not tell us that the thing is bouncing up and down on the incline, or that it's digging into the surface of the incline, or that it's shooting off the surface of the incline. All of those tell us that the acceleration in the y direction is equal to zero. So we're going to start from there. So solution. Newton's second law. I'm going to go ahead and take the time to write it vectorially real quick, just to remind you about what we were just talking about. And then I'm going to also write it down in terms of components. That means the summation forces in the y direction equals mass times acceleration in the y direction. The summation forces in the x direction is equal to mass times acceleration in the x direction. And I have no idea why I did y before x. And then the summation forces in the z direction is equal to mass times acceleration in the z direction. So that's one of the advantages of vectors, is the fact that you can write three equations with just writing one equation by adding the little vector symbols over top of it. Now, in addition to that, we know that weight is equal to mg, and that means it's 20.0 kilograms times 9.80 meters per second every second. And of course, 2 times 9.8 is 19.6. So 20 times 9.8 should be 196 newtons. Double checking my math just because there's a probability that I made some mistake and I want to avoid that. And I did get 196. So we've got that. Now I'm going to draw my free body diagram. As always, when you draw your free body diagram, you want to include a coordinate system. because the coordinate system is what allows you to decide which components are positive, which components are negative, all that good stuff. So this is going to be my y-axis. This is going to be my x-axis. I'm going to represent the 20 kilogram box as a dot. I meant to do a green dot, but I drew a black dot, so I'm redoing that now. Now, that is in fact the 20.0 kilogram box right there. Now, in addition to the 20 kilogram box, on the free body diagram, we got to put all the forces that are acting on it. So one force I know acting on it is the weight, and the weight is 196 newtons in the downward y direction. We also know that there's going to be a normal force in the upward direction, because the normal force is always perpendicular to the surface, and our surface is parallel, or excuse me, our surface is horizontal, and that means that vertical is perpendicular and therefore normal to the surface. So this is going to be my normal force, and I'm just going to call it N this time. Now, in addition to that, we have a vector that hasn't been adjusted such that it's parallel to an x or y axis. So it's I usually try to make sure I don't color them vectors like that in a color of red or blue if I'm using red for negative and blue for positive, or if I'm using red for negative and green for positive, make sure I don't color it green either. So I'm going to put a purple vector, and that's going to represent the force that's actually acting on it at 30 degrees, and that force is right here. It's 50.0 newtons is equal to F, and this is 30.0 degrees. Now, I need, before I can write out my summation of the forces equation, I need all the vectors broken into their components. So I first need to write this F vector in X components and Y components, and I can imagine my walk by walking from the tail of the purple vector to the head. If I walk along the x-axis, I have to go to the right, and if I walk parallel to the y-axis, I have to go up. Both of those directions are positive, so I am going to say that my x component is positive. For some reason, it just changed that color to some color that I didn't mean to be. So there it is. So the x component is in fact positive. That's my positive x component, and my y component is also positive. So I'm going to put there. In this case, since we're not really considering what's going on with the box as far as it moving left and right, there is something to be worked out left and right, but I don't have to do that at all because we're just asked about the normal force. So now I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction. Again, we weren't told anything like the 20 kilogram box is digging into the surface, or it's bouncing up off the surface, or it's jumping up off the surface. All of that suggests that the 20 kilogram box, even if it is moving perfectly horizontally, which means the velocity in the vertical direction is a constant, and in fact it's zero. So we're going to say, despite it being whether or not it's zero, the fact that it's constant means the acceleration is zero. So that's what we're using here. Now, I have to figure out what those components are. So I need to write out the sines and cosines. I'm going to go ahead and do that. I'll do it in purple down here. Sine, oops, I said I was going to do it in purple, but I did it in red. I'll do it in red, that's fine. So the sine of 30.0 degrees is opposite over hypotenuse. That's going to be F sub y over 50.0 newtons, and the cosine of 30.0 degrees is equal to adjacent over hypotenuse. That's going to be F sub x over 50.0 newtons. But as I said, I only need the y component. So I'm going to take 50 and multiply it by the sine of 30. And that gives me 25. So I now know that y component. What I can do now is the left-hand side of Newton's second law says that the force, the normal force N, which is pointing in the positive direction, so I could have written a plus next to it, or I can just leave it like it is. Both say that it's in the positive direction, so that's fine. Now I'm going to add to that the y component of F, which is positive 25.0 newtons, and then I'm going to add to that the y component of the weight, which is negative 196 newtons. And that's all the forces I see acting on it, except for, of course, there's obviously an X component to the force F. But again, we're ignoring the X component. I might actually, right after I finish this, I'll do something with that X component to help you understand what that's really meaning. And that'll be just another part. So now that I have that, I can say all of this is equal to 0, and that tells me that the normal force is going to be actually 196 minus 25. So if we were subtracting 25 from 200, it'd be 175, but we're actually 4 less than that. So it's going to be 171 newtons. So again, double checking my math, it's 25 minus 196 gives me 171, negative 171, but then I put it on the other side and it's positive 171. So the normal force in this case is 171 newtons. So you can see how in this case a component of force in the upward direction actually reduced the normal force from what would have been 196 newtons to 171. Remember, the normal force on a horizontal surface, if there's no other vertical forces acting, the normal force is just equal to the weight. In this case, we had a force pulling not only to the right but also upward a little bit, and because of that upward component it actually reduced the normal force. You've probably run into this before if you've ever had to try to push like a really heavy box on a smooth carpet or a smooth wood floor or even a smooth concrete floor. What you discovered is if you had any difficulty, meaning the box was kind of heavy, if you had any difficulty pushing that box onto that surface, inevitably your body would have figured out it was smart to not push down and forward, but rather to push completely horizontally. So you ended up tucking down a little bit and maybe putting your arms straight forward so that you were actually pushing exactly horizontal on the box. What happened there is your body realized, hey, I need every bit of strength I've got to push this thing. And when I'm pushing forward and down, I'm actually making the normal force a little larger. And since the friction force is proportional to the normal force, a larger normal force means I'm going to encounter more friction and therefore it's more difficult. So you slowly figure out that when I'm pushing down and forward like that, I'm actually making it harder. And when you slowly angle the force to horizontal, then the normal force just becomes the weight of the object. And that's about the best case scenario, unless you were able to reduce the normal force. But if you push it now with your arms perfectly horizontal, now you only have to deal with a horizontal normal force that's exactly equal to the weight. Now, if you were to still have difficulty when you leveled your arms out so that you're pushing perfectly horizontally, if you ran into still some problems, meaning it was too hard to push, you might have figured out, well, sometimes it's just easier to pull. And what you could do is, for instance, wrap a rope around the box. And if you pulled the rope horizontally, you'd need just as much force to pull it as you did to push it in the previous part. So if you were having problems pushing it, even when you were horizontal, pulling it horizontal might give you a little advantage because sometimes it's a little easier to pull things than it is to push. But other than that, you get no advantage. But if you start lifting up, so instead of the rope being perfectly horizontal, the rope is in an upward direction like this one. In this case, you're actually lifting the box just a little bit. You're actually tending to rotate it, but we're not dealing with rotational motion yet. But you are tending to rotate it, and that can actually reduce the normal force on it a little bit. And since the friction force is proportional to the normal force will actually decrease, and the friction force will decrease by you pulling up on it. So that's a little bit safer or a little bit easier as well. So hopefully that helps. Now, in addition to this, what if the friction on the box was zero? If the friction on the box was zero, we could go ahead and calculate what the acceleration of this box would be. So I'm going to say part B, as soon as I get my pen right, B. If the friction between the box and the surface is zero or negligible, then the acceleration can be determined. So how do we do that? Well, the summation forces in the x direction is equal to mass times acceleration in the x direction. That's the only acceleration that we're dealing with because we already said the y acceleration was zero. So now in this case, I look and my free body diagram only shows one force acting in the horizontal direction, and that's the x component of the force F. And the x component of the force F is F sub x is equal to 50.0 newtons times cosine 30.0 degrees. And that gives you 43.30 newtons in the positive direction. So in this case, I'm going to say 43.30 newtons is the only thing on the left-hand side of Newton's second law in the x direction. And on the right-hand side is the mass of the box, which is 20.0 kilograms times the only acceleration. So I'm not going to bother putting an x on it. I'm just going to call it A. And in this case, we get that A is equal to 43.30 newtons divided by 20.0 kilograms. And that gives me 2.165 meters per second every second. And I want to reiterate to you guys that now that we're into the dynamics portion and we're studying how to make things accelerate or reach a certain velocity, that doesn't mean we're now out of the woods on kinetics or kinesiology, or I should say, on kinematics. That just means that you still have to know that stuff too. So, for instance, I could follow this up and say, if it started from rest, after 3 seconds, how fast would the object be going? Or after 1 second, how fast would it be going? Or I could say, how far would it have traveled after 4 seconds if it started from rest? All of those questions that we learned about kinematics are all still fair game, but now we have learned that we could have used the x components of these forces to figure out that the acceleration of this block in this scenario is 2.165 meters per second every second. That means if it started from rest, after 1 second, it'd be going 2.17 meters per second. After 2 seconds, it'd be going 4.34 meters per second. After 3 seconds, it'd be going 3 times 2.16 or 2.17, so on and so forth. So that's some of the kinematics that we're talking about. Anybody have any questions on that one? Not getting any questions. I'm hoping that's a good thing. I hope that means that you guys are understanding it. Let's go ahead and try the next problem now. This one's sort of, there's not really, well, there's something like it in the book, but this is one I work just about every semester, so you can find a lot of iterations of it on my YouTube channel. But what I have here is a chain of boxes on a frictionless surface. Uh, Basically, what's going on is we have a 10 kilogram box that's connected by a rope to a 20 kilogram box, and that 20 kilogram box is connected by a rope to a 40 kilogram box, and then that 40 kilogram box is being pulled by a 200 Newton force to the right. And I want to know what is the acceleration and tension. So basically what's going on here is I have this object that you can sort of look at as if it's one big object whose mass is 70 kilograms. Notice 40 plus 20 plus 10 is 70 kilograms. Or we can look at it as three independent little bodies and work that out. In fact, to solve this problem, if you want to actually know the tensions in the ropes, you can't treat the 10 kilograms plus the 20 kilograms plus the 40 kilograms as one object, because then the tensions in the rope would be internal forces and they don't appear in Newton's second law. Instead, what you have to do is write a Newton's second law for each part. And in general, I always recommend, at least my starting off students like you guys are, I always recommend that you write a one, a free body diagram for each body, and two, a F equals ma for each dimension and each body in the object. So we're going to do a little bit of both right now. So let's solve it as follows. Here's our solution. So again, it's frictionless. And we're assuming that the train of boxes is not bouncing up and down. It's not digging into the surface just like we did on the previous one. We're really assuming here that there's no motion in the vertical direction, so the acceleration in the y direction will be zero, but the acceleration in the x direction can very much be different than zero. Okay, so what we know is that the summation of the forces according to Newton's second law is equal to mass times acceleration as a vector equation, and that gives us, of course, the x equation and the y equation and even the z equation if we want. I'm going to assume that x is to the right and y is up. That's going to decide all our signs. And first off, I'm going to treat the object as one big body, and that will allow us to figure out what the acceleration of the whole thing is. And then we can compare that later to the accelerations we get by treating the separate parts. So first off, one, treat the train of boxes, whoa, like it is one 70.0 kilogram object. So what do we mean by that? Well, what we mean by that is here's our x-axis, here's our y-axis, uh, here's my 70.0 kilogram object. The only forces I have acting on it, in fact, is this F equals 200.0 newtons. We also have, of course, acting on it a normal force, which I'm just going to call N, and we have a weight W equals 70 times 9.8 is 686 newtons, like that. So the summation forces in the y direction equals mass times acceleration in the y direction. We're assuming, like I said, the acceleration in the y direction is zero. That means normal force minus 686 newtons is equal to zero. That tells us the normal force is equal to 686 newtons. We weren't asked that, but now we found it, and it's just, more practice. Now I'm going to take the summation of forces in the x direction, and that's equal to mass times acceleration in the x direction. But again, that's the only acceleration, so I'm just going to reduce that and call it a. So the summation of forces in the x direction really only has one force because it's frictionless, and that's the 200.0 newtons. But on the other side, we've got the total mass, which is 70.0 kilograms times A, and that tells us that the acceleration is equal to 200.0 newtons divided by 70.0 kilograms. That gives me 2.857. Oops. Now that's 4 sig figs divided by 3 sig figs, so we should only get 3 sig figs, and that's 2.857, 7 being a non-significant figure, and a newton divided by a kilogram is a meter per second per second. And that's the acceleration that we're asked for. So that's the acceleration of the whole system. That means basically if and we're going to make this assumption that the ropes are not going to become slack, they're not going to stretch, they're not going to break, they're not going to, you know, become so slack that they get a loop in them. So that in fact, when the 40 kilogram mass moves 1 inch to the right, the 20 kilogram mass and the 10 kilogram mass is going to move 1 inch to the right. If the 40 kilogram mass moves 1 inch to the right in 1 second, then the 20 kilogram mass is going to move 1 inch to the right in 1 second, and the 10 kilogram mass is going to move 1 inch to the right in 1 second. That means that the velocity of the 40 kilogram mass is exactly equal to the velocity of the 20, and it's exactly equal to the velocity of the 10. Similarly, if the box moves 1 inch in the first second and 2 inches in the second, if the 40 kilogram box does that, then the 20 kilogram box is going to do that. And if the 20 kilogram box does that, then the 10 kilogram box is going to do that. And since we're imagining going a distance of 1 inch in 1 second and then 2 inches in the next second, that's clearly an acceleration. And what we discover is that the acceleration of the 40 kilogram box has to equal the acceleration of the 20 kilogram box, and that has to equal the acceleration of the 10 kilogram box. That's sort of going through the thought process of using the fact that the ropes that connect them do not stretch, do not break, and do not get slack means that the motions basically are such that the acceleration of one is the acceleration of them all, the velocity of one is the velocity of them all, and so on. So hopefully that helps. Now that we have this, we know that the acceleration of each of the blocks is in fact 2.857 meters per second every second to the right. Now I'm going to treat each box independently. Two, treat each box independently. Now I'm saying independently, but it's obviously not independently because the rope is tethering them all together. I'm just meaning that I'm going to draw a free body diagram for each one and you F equals MA for each one. And that's what I'm going with here. So let's draw our coordinate axes. The coordinate axes are all going to be like this. X is to the right, Y is up. And I'm going to first off draw the one for the 10 kilogram mass. So this is 10.0 kilograms. What we have acting on it is a weight that is 10 times 9.8. So that's 98.0 newtons downward. But we also have a normal force in 10 acting upward. And we have a tension that, according to the 10 kilogram box, all it knows is it's got a rope attached to its, what we're looking at is the right hand side, and that rope is pulling it to the, what we call the right direction, to the right. So, according to it, it has a force that I call a tension, and that points to the right, and the right is a positive direction. So, I'm going to draw a green vector, and I'm going to say T10. So with that, I get the summation forces in the y direction equals mass times acceleration in the y direction, which is 0. This tells us that N10 is equal to 98.0 newtons. Not that we were asked it, but I just wanted you to recall, now that we've done all this, you should understand that this is the way it goes. Now I'm going to do the summation forces in the x direction equals mass times acceleration in the x direction. In this case, I'm going to say T10 is the only force acting, and it's acting to the right, so I'm going to call it positive. But I'm going to say that is equal to 10.0 kilograms times the acceleration A. And again, I don't have to subscript it because I just finished explaining to you how the acceleration of one is the acceleration of them all. Okay. In fact, at this point, I could plug in that 2.857 meters per second every second, and that would give me that the acceleration, or excuse me, that the tension is 28.57 newtons. And that actually is going to be the right answer. We just can't see it yet unless we use the A. So I'm just going to put a little underline by that and remember that we're going to use that in a second, and I'm going to call it equation 1. Now I'm going to draw another coordinate system, and this one's for the 20 kilogram mass. Now this one has a normal force in 20. It has a gravitational force that is obviously 20 times 9.8. We just discovered that was 196. But it also has a tension. According to the 20 kilogram box, there's a rope between it and the 40 kilogram box, and that rope is pulling it to our right. So it interprets that as a force pointing to the right, and I got to make this axis a little bigger to see it. So I'm going to extend this axis a little bit, extend this vector a little bit so we can see that. Now, what I have here is a green vector because it points in the positive direction, and that is the tension in the 20, in the rope that's attached to the 20 kilogram. But the 20 kilogram mass says not only is there a rope in front of me that's pulling me to keep up with the 40 kilogram box, but there's a rope on my backside that's trying to slow me down. That rope is the same rope that we used in the previous problem, and therefore that tension should be T10, but notice it's pulling to the left, so I'm going to have to draw that one as a negative, and that's T10. So I can do the same thing again. The summation of the forces in the y direction equals mass times acceleration in the y direction, but the acceleration in the y direction is 0. So in this case, I'm just getting N20 is equal to 196 newtons. So that again is a result that we weren't asked for, but I showed you just for completeness. Now we're going to take the summation of the forces in the x direction equals mass times acceleration in the x direction. Again, all the accelerations are the same, so there's no reason for any subscripts. But in this case, we have T20 minus T10 is equal to 20.0 kilograms times A. And that is another equation we can make use of, and I'm going to call that equation 2. Now I'm going to do the 40 kilogram box again with a little coordinate system. I'm going to draw a little bigger this time in case people were having difficulties seeing it last time. So there's my y-axis. And this time again, we have the 40.0 kilogram mass. We have acting on it a normal force that I'm going to call N40. I have acting on it a weight, which is 40 kilograms times 9.8 meters per second. And that gives me 392. Now, in this case, the 40 kilogram box says, hey, there's this force of 200 newtons pulling me to the right. So I'm going to write that on there. That's the 200.0 Newton force. And then it also says, hey, if you're thinking from the perspective of the 40 kilogram box, it says, hey, there's this stupid rope tied to my back and that's pulling me backwards. That happens to be the same tension T20 that we ran into before, but now it's acting in the negative direction. So this time I'm going to write it as T20, and notice the T20 is negative. Notice also that on the diagram for the 10 kilogram, the tension is T10 is acting to the right, whereas the diagram for the 20 kilogram, the T10 is acting to the left. That's very normal for tensions. This is the process you need to go through and sort of memorize it until you can make sense of it yourself. But I think me arguing exactly what the box's feels and experiences are, what a person sitting in the box would feel or experience or conclude, I think that's enough for you to understand exactly why the T10 is pointing to the right in the first diagram and the left in the second, and the T20 is pointing to the right in the second diagram, but to the left in the third. Hopefully that's the case. If not, just remember the process, and over time, your brain can work it out, or you can just ask me some more. I'm going to go ahead and do the y-axis again, even though we don't really have to do it. The summation forces in the y direction equals mass times acceleration in the y direction, but the acceleration in the y direction is 0. So I'm going to say this concludes that N40 is actually equal to 392 newtons, which is exactly what we expected. Now I'm going to do the summation of the forces in the x direction equals mass times acceleration in the x direction. Again, we don't need any subscripts, but this time we've got 200.0 newtons minus T20 is equal to 40.0 kilograms times A. Again, A does not need a subscript. This is going to be called equation 3. So what I can do is I can take equation 1 and plug it into equation 2. So 1 into 2, and that gives me T20 minus 10.0 kilograms times A is equal to 20.0 kilograms times A. And I'll call this equation 4. Now I can solve for T20, and that gives me T20 is equal to, notice all I have to do is add 10 kilograms times A to both sides. That's going to give me 30.0 kilograms times A. I'm going to call that equation 5. So now I plug 5 into equation 3, and that gives me 200.0 newtons minus 300 kilograms times A is equal to 40.0 kilograms times A. Oh, that was supposed to be 30. I called it 300 kilograms. It's 30.0. Sorry about that. Make sure that dot's in there. This is supposed to be a 30 kilograms. Okay. Now you can see that the 30 kilogram, if I pulled it to the other side, it'll become 70 kilograms, and you'll have 200 newtons equals 70 kilograms times A, and that allows you to conclude that A is equal to 2.857 meters per second every second, which is exactly what we got by doing it the first way. But by doing it the first way, that's the only result we could get. But now you can go back that now that we know these different versions of the acceleration, or excuse me, these different versions of the equations for the tension, we can now go back and solve for the tension. So for instance, the tension is supposed to be 10 kilograms times A, and A is 2.857. So we can conclude that I'm going to write it over here in the area 1 just because I don't want to write it on another page because you might lose it. Actually, no, I'll do this. I'm going to take this stuff right here and I'm going to copy all this to the next page. Paste. So now we can see it here. Now I didn't need this part, so I'm going to go ahead and erase it. So now that we have this, I can say from 1, we have T10 is equal to 10.0 kilograms times, so this is 1 and A, meaning the solution we just made for A, 2.857 meters per second gives me 28.57 newtons is the tension T10. And I didn't write that 10 separate from the T very well, so I'm doing it again. So the tension in the rope is 28.57, which notice is just the amount that you need just to accelerate the 10 kilogram mass. In the next case, you're not going to find that the T20 is just enough to accelerate the 20 kilogram mass. It has to be enough to accelerate the 20 kilogram mass and the 10 kilogram mass. So now we can look at equation 5. So using 5, oops. So from 5 and A, we get T20 is equal to 30.0 kilograms times 2.857 meters per second. Now see the 30 kilogram right there is exactly the part where I'm telling you the T20 is not just enough force to accelerate the 20 kilogram. It's actually got to be enough to accelerate the 20 plus the 10. That's why we have the 30 there. So when I multiply 30 times 2.857, I get 85.71 newtons is equal to T20. So hopefully this taught you a little bit about how, for instance, trains and tension and ropes and stuff like that work. Now that I have the tension T10 and the tension T20 and the acceleration of the train of boxes, I've now completed the whole problem. Anybody have any questions on that one? Okay. There's another problem that we normally call the Atwood machine. I'm going to do that rather quickly, and I'm going to do it only with symbols because we only got about 10 minutes. But I want to work that, and that'll complete basically everything from chapter four. But to be honest with you, all the stuff I've been doing has been prepping you for chapter five. So chapter five is going to take a lot less time. So let's go on with this would be called example seven. Find A and T. So that seems a little not helpful, but it'll explain itself in a second. So first off, what I'm going to do is draw a pulley, and that pulley is going to look like this. I'm using the program's ability to make my shapes that are bad into good shapes. So I have a pulley. Now I'm considering this pulley to be massless. What does that mean? In the physics world, there's no such thing as massless except for photons and some other rare particles and space and stuff like that. But in the physics realm, when we say something's massless, really all it has to be is at least a factor of 10 lighter than everything that you're going to deal with from a mass or force standpoint. So if you're thinking about its mass, then it's at least, or it's no bigger than 1/10 of any of the other masses that are relevant. If we're talking about forces, then it's no more than 1/10 of any other forces we're dealing with. And sometimes those masses and forces aren't just the masses and forces you see. Sometimes they're the difference of masses or the sums of masses, all sorts of stuff. But what we have here is a pulley. We can imagine it having a radius r, for instance. Ooh, I got to be careful with that because I'm still in the make my drawings neat thing. The r is not going to be relevant to us at all, but what I am going to do is I'm going to imagine that I have a huge box up here very, very high, and because it's huge, I'm going to make its mass capital M. And then way down here, sitting on the ground, is a small mass, little m. Now, I've drawn it like this to give you the idea that it's probably going to result in the mass big M going downward, hitting the ground while the mass little m goes up. And remember, if we assume that the mass of the pulley is zero and the mass of the string is zero, then and that the string doesn't become slack or stretch, then if I move the mass big M down 1 inch, then the mass little m will go up 1 inch. Similarly, if I move it down 1 inch in 1 second, the little m will go up 1 inch in 1 second. So that means their velocities are the same. Similarly, if I pull it down 1 inch in the first second and 2 inches in the second, then the acceleration of the mass big M will be exactly the same as the acceleration of the mass little m, because the mass little m will go up 1 inch in the first second and 2 inches in the second second. So that tells us that all those accelerations are the same. Not only that, if you imagine me trying to pull down on that big mass on the right, if the pulley had a mass, then me pulling it, the big mass M downward, would require some force to even make the massive pulley rotate. That would make the tension between the big M and the pulley bigger than the tension between the little m and the pulley. So the tension on the left would be smaller than the tension on the right when I'm pulling the big mass, big M downward, if the pulley had mass. So since the pulley does not have mass, that means the tension in the left is equal to the tension in the right. That's a complicated thought process. I highly recommend you pausing the video, going back to the spot in the video, pausing it, watching it, listening to it again, and until you get it. So let me explain it again. If we imagine that pulley was made out of, let's say, a 12-foot long, 12-inch diameter concrete pole, then that sucker would be pretty heavy. And you could imagine that just rotating it would take a lot of work. So us trying to rotate it by pulling down on the mass big M means that I'm going to have to pull very, very hard on the mass big M, because not only am I lifting the mass little m on the other side up by pulling down on the right side, I'm also rotating that very, very, very heavy uh, cylinder. So that's the deal. So we're going to say the tension on the left is equal to tension on the right. Not only that, I'm going to try to make sure that my coordinates are consistent, so that if I consider down on the right hand side as positive, that's the same thing as up on the left hand side being positive. So now I'm going to draw my free body diagrams. I'm going to call this the positive y direction, and I'm going to put a mass little m right here. And of course, that means the force downward would be the weight of little m, which would be little mg, and the force pulling it up would be the tension T, and I don't have to subscript the tension because I just finished telling you, making that argument to you, that the two tensions have to be equal. So that's the entire free body diagram for the little mass. So if I do the summation forces in the y direction equals mass times acceleration in the y direction, and ditch the subscript on the a for the reasons that we've talked about several times now, then all I'm going to get is T minus mg is equal to MA. So I'm going to call that equation 1. Now, if you follow that Y upward, you'd get to the pulley, you'd curl around it, and then you start going downward. So over here, I'm going to draw the coordinate system for the big mass M, only this time I'm saying Y is pointing down, because that's what we have to do to make the coordinates consistent. If you didn't, you'd have to make another equation relating the acceleration of one equal to the negative of the acceleration of the other, or something weird like that, and you just don't want to get into all that. So the mass is big M. In this case, the weight is pointing in the positive direction, so I'm going to say right here, this force is green because it points in the positive direction, and the weight is capital M times G, but the tension is acting in the upward direction, and that is the red vector. So this one's going to give me the summation of the forces in the y direction equals mass times acceleration in the y direction as mg minus t is equal to ma, and this is going to be equation 2. So if we add equation 1 to equation 2, that means add the left sides to the left sides, and the right side to the right side. That's going to give me T minus mg plus mg minus t is equal to ma plus big Ma. Obviously, you can see that the t's cancel out here, and I can factor out the g's and the a, and I get m plus m times g is equal to m. Oh, excuse me, that's big M minus little m. Sorry about that. I was looking at the other side and wrote down what that was. So this would be big M minus little m times G. But on the right side, it's going to be little m plus big M times A. Therefore, we know the A is M minus M over M plus M times G. And that is the acceleration. Now that we have that, all we have to do is plug that A in equation 1 or equation 2 and solve for T. I'll tell you that T is equal to 2 M over M plus M times mg. That's actually what it is. You can go ahead and work that out yourself for extra credit, but we are done. If anybody has any questions, I'll wait for the last person to leave in case you don't, in case you do. But go ahead and chat me your first and last name. Don't forget to add async on the end of it if you're from my other class. You guys are free to go. Thanks for coming. I hope this all helped. Watch out for my email about the test, and hopefully you remaining people that hadn't done your face-to-face test one, please get that done. Remember, it's on chapters one, two, and three, but only part of chapter three. You're welcome, Ely. Ellie, Eli. I can't remember. Beth or Darius, you have any questions? All right, it looks like they might not be here, so I'm going to go ahead and stop sharing. This will give them a little bit more time in case they do have questions. It doesn't look like they do. Darius and Beth are evidently. Okay, Darius is gone. How about you, Beth? Did you have a question? She might not be here. All right, well, thanks again, everybody. Good night. Bye bye.